So a third sorting algorithm that I'm going to go over is quicksort. So for quicksort, what you do is first you want to pick a pivot value, and there's multiple ways you can do this. And then after you pick a pivot, you want to partition the array by moving elements less than the pivot to the left side of the array and moving elements greater than the pivot to the right. And then after you partition the array, you want to repeat this quicksort algorithm for the left and right halves. So if we look at this array here, we want to pick a pivot. So for simplicity, I'm just going to choose the first element, which is going to be 11. So first, I'm just going to take the pivot value and move it to the side. And then now that we have our pivot value, we want to partition the array. And there's multiple ways you can do this. One common way is to have a lower and upper pointer. So I'm going to set the lower pointer to the first index, and I'll set an upper pointer to the last index here. And then first, I'm going to start with the upper pointer, and I'm going to move it until I find a value that's less than the pivot. So we see here, the upper pointer is already pointing to 5, which is less than 11. And now I'm going to move that value to the place where the lower pointer is pointing. So I moved it here. Now that I moved it to the lower pointer, I can increment this lower pointer. And I want to increment it until I find a value which is greater than the pivot. So I see that low is pointing to 20, which is greater than 11. So now I'm going to move 20 and move it to where the higher pointer is. And then I'm going to turn my attention back to the higher pointer and move it until I find a value which is lower than the pivot. So I move it here. I see, okay, 20 is not lower than 11, so I move it here. Okay, 7 is lower than 11. So again, I move 7 over to the lower pointer. And then I move this lower pointer now. Is 11 greater than 11? Nope, so I move it again. Is 6 greater than 11? Nope, I move it again. And then once I move it here, I see that the lower pointer and higher pointer have now met. And once this happens, you stop incrementing the pointers, and we can just move this pivot value back here. So after we do this, we can see that this part of the array, right here, we can see that this part of the array, all the elements here is less than the pivot, and all the elements here are greater than the pivot. Once we've done this, we look at each half of the array, this half and this half, and then we redo the quicksort algorithm on it. So we'll pick a new pivot, partition this one, and do it again. So this is similar to merge sort in that you kind of start splitting the array smaller and smaller, and then you're kind of running the algorithm on smaller and smaller subsections of the array. So now I want to talk about choosing a pivot for quicksort. For our example, we chose a pivot to be the first value of the array, which is not always optimal. When choosing a pivot, you want to choose one such that when you partition the array, there's roughly an equal number of elements to the left and right of the pivot. This makes it so the number of times you kind of call the quicksort algorithm, it'll only be log of n times for log of n layers, similar to merge sort. So if you look here, if you look at this array, if we used our method of choosing the first element, which is 2, after we partition the array, this section would effectively be the right half because all of these elements are already bigger than 2. And then there wouldn't even be a left half. And then after we call quicksort again, if we call quicksort on this part of the array now, 3 would be the pivot. And then this would be the right half of that section, and there wouldn't even be a left half again. So essentially we'd have to call the quicksort algorithm n times for every element in the array, so which is not great. And there's some ways to counteract this. So instead of choosing the first or last element to be the pivot, you could choose the middle element, but sometimes that also has some flaws. So the best way is to choose a random pivot. And this makes it very likely that the pivot you choose, it'll be somewhat in the middle, one of the middle values in the array. And if we think about the complexity for quicksort, we saw that for a bad pivot, if it doesn't partition the array well, there will be n layers, and then for each layer, when we partition it, we're going to have to loop through every element, so that'll be O of n. And therefore, the worst case for quicksort is O of n squared. But if we choose a good pivot, then on average, quicksort will only have a log of n layers because it'll tend to split the array by halves, similar to merge sort. And it will still be O of n for partitioning, which makes the total average case complexity O of n log n. So we see that if we choose a good pivot for quicksort, it's O of n log n, which is pretty good. And then if we think about this, if quicksort is stable, we see that it isn't, because depending on how we partition the array, the values get swapped around. So for instance, if you go back in the video, you see that this fancy 11 was to the left of this 11 in the beginning, but after we partitioned it, this 11 ended up to the right of this 11. There are ways to make quicksort stable. However, most implementations of it is unstable. One good thing about quicksort is that it is in place, unlike merge sort, because it doesn't have to use any extra memory. So to summarize the three sorting algorithms, we see that selection sort has the worst complexity. It's O of n squared in all cases. It is not stable, but it is in place. For merge sort, we see that it's O of n log n in all cases, and it is stable, but unfortunately it is not in place since it has to use extra memory. And for quicksort, on average it is n log n, but it can be worst case O of n squared if you choose a bad pivot. It is in place, but it's not stable.